Hello everyone, and welcome to this session where we will use the structural analysis program Ftool to analyze the statically indeterminate beam shown in the figure on screen. I will first briefly explain the hand solution of the problem using the consistent deformation method and the moment area method. Then I will demonstrate the solution procedure using the computer program. After performing structural analysis of the beam, I will ask the program to draw its shear force and bending moment diagrams, as well as its deformed shape. While studying indeterminate structural analysis, you should always practice solving your examples and problems by hand. Once you are done with the manual solution, you can use a computer software in order to check the correctness of your hand solution and to enhance your computer skills. The problem under consideration is stated using the standard international system of units. The beam at hand is an 18-meter long continuous beam that is made up of 3 spans. The concentrated load is located at the middle of the central span. Settlements take place at supports A and E with unequal amounts of 15 millimeters and 20 millimeters respectively, rendering the actual beam unsymmetrical, which is a very important thing to understand here. The actual beam is symmetrical in terms of loading and geometry, but the settlements render the beam unsymmetrical. We are given the modulus of elasticity and the moment of inertia of the beam, as these material and cross-sectional properties will be necessary during the solution of the indeterminate beam with specified support displacements. A quick look at the beam shows 5 reactions and 3 equations, rendering the beam statically indeterminate to the 2nd degree. The question requires us to find the reactions, but we will also draw the shear force and bending moment diagrams, as well as the deflected shape using the computer program. I will briefly explain the hand solution using the consistent deformation method and the moment area method before I solve the problem using Ftool. We will select the redundants to be reaction at A and reaction at E, where the support displacements are specified. Although the actual structure is not symmetrical due to unequal amounts of support displacements at points A and E, the primary structure is symmetric in terms of geometry and loading. The 2 secondary structures are symmetric in terms of geometry, which will help us shorten the manual solution by drawing only the primary structure along with 1 secondary structure instead of 2, and then making use of the symmetry and the Maxwell's reciprocal theorem to obtain the required deflections and linear flexibility coefficients. On the primary structure shown on screen, we will draw a tangent to the deflected shape at point C, which happens to be a horizontal line due to symmetry. Then we will use the moment area theorem number 2, as well as similar triangles to calculate the deflection at point A, which is equal to the deflection at point E due to symmetry. On the secondary structure, we will draw tangents to the deflected shape at points B and D. Find the linear flexibility coefficients FAA and FAE using moment area theorem number 2 and similar triangles. Then using Maxwell's reciprocal theorem, the linear flexibility coefficient FEA is equal to the linear flexibility coefficient FAE. The linear flexibility coefficient FEE is equal to FAA due to symmetry. Using the consistent deformation method compatibility equations, we can find the reactions at point A and E, with positive answers indicating that the reactions are in the same direction of the unit load applied on the secondary structure number 1. Note that the compatibility equations are equated to the amounts of specified displacements at the points A and E. Had there been no specified displacements, the 2 equations shown on screen would have been equated to zeros. Let's now proceed to the computer program solution. Start the program Ftool and open the metric template that we have created in earlier sessions. If this is the first video that you are watching in this series, then I strongly encourage you to go back and watch previous sessions in order to keep up. The beam that we are trying to model is 18 meters long, has 3 spans, with a modulus of elasticity equal to 200 gigapascals and a moment of inertia equal to 90 times 10 to the 6 millimeters to the 4. So we're going to activate the keyboard mode here and then click on Insert Nodes and draw my nodes one by one. I have one node at 0, 0. Then I'm going to have a node at 5, 13, and 18. If only some of the nodes are visible on your screen, then you can click here on Fit World on screen to have all the nodes visible. I'm going to deactivate the keyboard mode and use my Insert Member command to draw my beam segments one by one. This here is the first segment, second, and the third. Next, I'm going to click on Material Properties. I've shown you how to create a new material in this section in previous sessions. So I'm just going to add here the value, which is 200 times 10 to the 3 megapascals. Select all my beam segments and assign this value to these beam segments. Next, we're going to go to the cross-sectional properties and assign a value for the moment of inertia equal to 90 times 10 to the 6 millimeters to the 4. I want to emphasize the fact that I am adding a very large value for the cross-sectional area in order to eliminate any axial deformations in this problem. I'm going to again select all my beam segments and apply the current settings to these segments. Next, we're going to create our support. I'm going to select the 3 supports that will be rollers according to the figure of the problem here. You can see that A, D, and E are rollers while B is a pin. So I've selected all 3 roller supports or roller to be supports, and then here I'm going to fix their conditions. For a roller support, we just need a reaction in the Y direction. And I'm going to apply these conditions to the selected nodes. These are our roller supports. And next, for the fixed support, I'm going to select this node and add a constraint to the x-axis here and assign this one here. I want to add my load, which happens to be a concentrated load located mid-span between B and D with a magnitude of 90 kilonewtons. So we're going to add a node here in the middle. I'm going to activate the keyboard mode again and add a node at 9 meters. Select that node and go to loads. I have defined a load and called it load number 1 and assign a value in the negative Y direction equal to 90 kilonewtons. I'm going to assign that value here. The last step is to define our support displacements. So we're going to go back here to support conditions, select support A, and add a prescribed displacement in the Y direction equal to minus 20 millimeters. Apply. And to point E, actually I have 15 millimeters here, so I'm going to change that to minus 15 and assign it again. And I have a 20 millimeter settlement at point E, so I'm going to select the last support, insert the value with the correct sign and the correct location. It's in the Y direction, and click on Apply. Now we are ready to view our results. I like always to click here on the axial force, since we don't have any axial forces in this problem, just to come here and say show the reaction values, where you can see the reactions, and you can compare these reactions to the ones that we obtained using the hand solution. They are identical. Next, we can click here on the Actually, we will remove the reactions first for clarity. I'm going to remove the values and the reaction symbols and show here the shear force diagram, then the bending moment diagram, and finally the deflected shape. The deflected shape, we can click here on the vertical displacement values in order to see the values at different locations of the beam. This concludes our session. Thank you very much for being with me, and I will see you in future sessions.